Divikan here with another question bank question on work, energy, and power. This is topic 2.3 in the syllabus. We're back on that bus. We're on a bus that's going up a hill. It's traveling at a constant speed of 6.2 meters per second along a section of road that's inclined at an angle of 60 degrees to the horizontal. Now, the fact that the bus is moving at a constant speed is very important. It means that it's not accelerating, which means that all the forces on the bus are in balance. And we want to find the total power output of the engine of the bus. The total power output of the engine of the bus is 70 kilowatts. And the efficiency of the engine is 35%. We want to calculate the input power into the engine. Well, we know how to calculate efficiency. It's 100% times the ratio of the output power to the input power. Now the efficiency is 35%, so if I take that and divide it by 100, I get 35 over 100 equals 70 over my input power. Now this I can solve with cross multiplication, but I don't have to, because take a look actually. 70 is twice 35, which means that the input power has to be twice 100. So the input power is 200 kilowatts. All right. The mass of the bus is 8.5 thousand kilograms. Determine the rate of increase of gravitational potential energy of the bus. Well, the bus is going up, so it's gaining gravitational potential energy, and we want to find that rate as a power. So basically, we want to find how much gravitational potential energy it gains every second. Now we know that the gravitational potential energy can be calculated as mgh. The mass of the bus is straightforward. Acceleration due to gravity is straightforward. The amount of height that the bus gains in 1 second, not as straightforward. Let's start by drawing a triangle representing the slope. We know that the bus is traveling along the slope at a rate of 6.2 meters per second. And we know that the slope is 6 degrees. Using that information, we can actually find the vertical component of this triangle, which tells us the rate at which the bus gains height. That's 6.2 sine of 6 degrees, which works out to 0.6481. Taking that over here, we get the mass, 8.5 times 10 to the third, acceleration due to gravity, and that rate, 0.6481. Punching that into our calculator, we get 5.51 times 10 to the fourth, watts, or to keep in line with the kilowatts we were working with earlier, that's 55 kilowatts. Okay. So the bus gains 55 kilowatts of gravitational potential energy. The bus is gaining 55 kilojoules of energy, gravitational potential energy, every second. So the power input into its gravitational potential energy, 55 kilowatts. Part D says to use your answer to Part C, 55 kilowatts, and the data in B to estimate the magnitude of the resistive forces acting on the bus. We know that 55 kilowatts go into the gravitational potential energy of the bus. We know that 70 kilowatts are available, that implies that the difference is going to fighting resistance. So the power lost to friction is that difference, 70 take 55, 15 kilowatts. And we can use that to find the force of friction, because if you're moving in a straight line with a constant velocity, the power you need to supply to fight friction is the force of friction times your velocity, and we know that power now. So F is P on V. That's 15 kilowatts divided by 6.2 meters per second. And that gives us 2.42, not newtons, kilonewtons. Kilonewtons because we had kilowatts, 15 kilowatts. Oh man, my pen is not enjoying what's going on. Okay, 2.42 kilonewtons. All right, we're getting there. Hang in there. Now the engine of the bus suddenly stops working. Newton's third law is going to tell us, Newton's first law is going to tell us that the bus is going to keep rolling for now while it still has inertia. Momentum, while it still has momentum. We want to determine the magnitude of the net force opposing the motion of the bus at this instant when the engine stops, so the driving forces quit. Now it's tempting to say that the net force is going to be simply friction, because friction is what's causing the bus to roll to a stop. But it's actually a little bit more complicated than that. Let's zoom in a bit and see if we can take a second look at that force diagram that we saw earlier. Here's the ramp. There's our weight. There's our normal force. And there's our force of friction. There's no longer a driving force. But the weight is not quite in line in the same Cartesian plane as the normal force and the force of friction. So what I'm going to do is I'm going to break the weight up, not into a horizontal and vertical component, but into a perpendicular and parallel component. The perpendicular component, shown here, should cancel with the normal force. If it doesn't, then we have a problem. That means the bus is taking off or crashing into the ramp and sinking through it. Neither of these are what's actually happening. So the perpendicular component of the weight cancels with the normal force, leaving two forces to add together to give us our total force. One of which is the force of friction. The other is this parallel component of the weight here. To find that, let's zoom in a little more. We know what the weight is. Come on now. It's okay, let's try down here. 8.5 times 10 to the third kilograms times 10 meters per second squared. That's 8.5 times 10 to the fourth newtons. But that's the weight. We want this little corner in here. That's going to be 8.5 times 10 to the fourth times the sine of 6 degrees. Because that's our 6-degree angle right in there. That gives us 8.9 times 10 to the third kilonewtons. which is quite a bit more. Oh no, excuse me. That's 0.89 kilonewtons. Now they're both acting down the ramp, so we'll add the two together. That's the parallel component of the weight. So that's 2.42 plus 0.89. And that gives us a total of 3.31 kilonewtons. All right. The last part says to discuss with reference to air resistance the change in the net force as the bus slows down. Okay. Well, the air resistance is related to the speed. And this bus, as its engine cuts off, is going to continue traveling up the ramp, but it's going to go slower and slower and slower, which means that the force of friction is going to get smaller and smaller and smaller. So this term right here is going to disappear. So the net force is going to decrease, but not to zero, because this will have no effect on the parallel component of the weight. So that means that the net force will decrease over time to a minimum of 0.89. And then the bus will either get stuck on the ramp or it'll start rolling back down the ramp again.